transforms of the signals shown in this particular figure. I was using my surface, but it is not charged. So let me just discuss anyways. If you remember, the Fourier transform comes from, let me open the lecture, 5.2. Inverse Fourier. Okay, so this is the formula for Fourier transform. Okay, this is the formula for Fourier transform, that the function integrated over minus infinity to infinity, the function e to the minus j omega t dt. So the thing that we need to insert is the function and the limits. The good thing about the limits is that we can break this one into different time segments which suits our function. In this one, in this particular example, we can see that we can break it into two, one here and one between 0 to 1 and 1 to 2. From minus infinity to 0, it's already 0, so we don't need to care about this one. And from 2 to infinity, it's 0. So first of all, we can break it from 0 to 2. So instead of using minus infinity to infinity, we can just break it from 0 to 2, because ft, whatever the ft is between 0 to 2 only, right? Between 0 and 1, it's just 2, right? It's just 2, simple. So we can just put 0 to 1, 2 e to the minus j omega t. You get it? I think this is easier somehow to understand. We don't need to worry about, because the function's value is already given. We don't need to worry about ut or delta t between, because of the limit. Limit is already there, so we can just put 0 to 1, 2 e to the minus j omega t. Is that okay? Do you guys agree with this one? Can I have a raise of hands? Yes, thank you. You are recording it. Thank you. Okay. All right. We have 24. Okay. Most of you agree. Thank you. Unraise your hands. And between 1 to 2, we need to find the function. Where is it? That represents this particular line. So we use the 2-point formula or equation of line to get this function. This will be something negative, maybe negative 1 upon 2 t, something like that. So we just find that function, we place it in here for 1 to 2, and we have the expression ready to be integrated, and we can find the Fourier transform. So it's not difficult. We can use the tables very easily to find the yeah. Okay, by the way, if we are integrating, then we put the value. If you want to make use of the tables, we can then make use of ut and ut minus 1. If you're, yeah, so Jocelyn, your question, if you're using the tables, then maybe you need to express it in a form that is available in the table. The tables are properties. So yeah, 1 is also okay. 1 is also okay. So this means 2 can be fit. One's Laplace, one's Fourier transform is 2 pi delta omega. All right. So we can do that. And if this t as well, I think we can make use of. This is I'm not sure. I'm not sure. Maybe you can just check by putting the formula of no, by putting the lines equation in that integral and see if it is equal to this one. Otherwise, you have to place that t, or you can do the t times. So you can use this one as well, t to the power n. So the question here will have a function with t as well. Do you agree with this? That this is 2. So yes, this is actually like 1. So we can use this relationship. Okay. Then when we use this one, there will be some function depending upon t. So we can take t as t times. There is no t times. There's no t times. Maybe in the uh, yeah, this one. So we can use this one as well. Okay, so the the constant is 1. So the Fourier transform of 1 is this one. Okay, and if we multiply with t, it will be the derivative of the Fourier transform with the j to the power n. Okay, like this. So the derivative of this, I'm not sure what will be the derivative of impulse function. Okay, but the thing is that we can easily, where is it? We can easily place. We can easily place the function here as well by introducing the limits and do the integration and find the Fourier transform. The outlook may look different. Don't worry about that. As long as you're following the procedure, there is no issue. So the key point is you break it, you leave this part out, you leave this part out between 0 and 1, and then between 1 and 2, between 0 and 1 is 2. We can use the table between 1 and 2. There will be an expression. Find a relationship in the tables, and then you can do that. Similarly here as well, you can break it down from -2 to 1, from -1 to 1, and then 1 to 2, and you will have 3 different functions available for integration, and then you can integrate. Any question in this particular explanation? I'm not talking about solution, explanation. Any question, guys? Anyone on the messages? No. Nothing. Either you guys are doing a lot of good studies, or everything is clear, or otherwise nothing is clear. Because when nothing is clear, you cannot ask a question. So it could be any of these 3 possibilities. So same here as well, like between 0 and 1 will be 2, between 1 and 2 will be 1, between 0 to 2 will be 5t, I believe, 5t, 10 and 2. This can be expressed as e to the minus t between 0 and infinity. This can be expressed as 0 between 0 and 1, e to the minus t. Yeah, actually, we can break it down into e to the minus t and e to the plus t. This thing, if you look at this carefully, this e to the minus t absolute value is actually expressing both sides. Both sides. So this part is e to the minus t, and this part is e to the plus. Actually, this part is e to the plus t. So you can break this down between -1 and 1 as e to the t, and this one as e to the minus t. This one is between 0 and infinity. This one is between 0 and 1. This is the difference. And these can be easily done if you place the actual function in the integration. One question that we did last week was about integrating the triangular wave. Where is it? This one. This was something, a triangular pulse, which was actually part of this one. And Someone asked me later on, how did we get this one? How did we get these impulses? Okay, uh, we can do this usually just like keeping this function in the integration, or if you want to make use of the formula or the pairs or the properties, we can convert this into an expression. Basically, what we did is we differentiated this to get this one. Again, we don't need to do this every time. We can do it in this way, but we can also do it using the standard classical method of integration as well. So that's totally up to you. This one is basically the derivative of this function. Okay, just to somebody might ask that this is 1, so there should be 0. Actually, it is 0 between -1 to 0. It's a flat line. That's why the function is 0. Between 0 and 1, again flat line, so no slope, again 0. But between -1 and -1, like between the same time instant, the slope is actually, the derivative is the slope. Remember, dx by dt or dy by dt are like the slopes. But at a vertical line, what is the slope? It's infinity. And by definition, the impulse function is actually by definition infinity. Its amplitude is infinite. That's why it's not just a line here. There's an arrow. By definition, theoretically, this delta function is like the amplitude is infinity and the width is 0. That's why there is no limit here. -1 to -1. So that's how we get the delta function at -1 or at 0 or at 1. This is basically the change, the slope. The derivative at -1 is infinity, negative infinity, positive infinity. This is like going from positive to negative. That's why this is negative. This is going from negative to positive, or like lower to higher. That's why it is positive. Right? So far, so good. Okay. And if we talk about the next question, which is actually 7.7, in this one we are given the transfer function of a circuit. Let me just highlight again. Transfer function is a circuit representation that can be used to relate the input and the output. If you remember, the definition of transfer function is the ratio of the Fourier domain representation output over Fourier domain representation of the input. So H omega is equal to output omega upon input omega. This is the ratio. And remember, in the definition of transfer function, this is to be true. This is to be true. Assume all initial conditions are 0. And if you remember the distinction between Laplace and Fourier, in Laplace, we can take care of initial conditions. Let me take you to the Laplace transform tables. This one, we can take care of the initial condition. Can you see this? We can, in the Laplace, we can take care of the initial conditions, but in Fourier we cannot. So this particular question, if somebody asks you, let's say if somebody asks you which method to be used to solve this circuit, it could be any method. Okay, the distinction is, there are two distinctions between Laplace and Fourier. One is Fourier cannot handle initial conditions, Laplace can. Okay, Laplace cannot handle two-sided signals, -infinity to infinity, but the Fourier can. So can I ask you this particular question? Can we do using Laplace? Yes or no? Can we do this question using Laplace? Somebody already answered. Can use both. Huntington, can we? Can I ask you why? Why can we use both? Both. There are no initial conditions here, so shouldn't we use Fourier? Shouldn't we use Fourier because there are no initial conditions? its right side only. U of t. U of t showing is from 0 to infinity. So this is matching both conditions that Laplace can handle. Initial condition 0, no problem. There are 0, so there is initial conditions or not, doesn't matter for Laplace. For Laplace, it matters that it should be a right side signal or just the 0 to infinity, which is shown by U of t, right? But in Fourier, if suppose this was not given, suppose just cancel this signal, just cancel this. Where is it? Why can't I take shapes? Okay. So very. Suppose this is not given. This is not given. Which one will be used? Laplace or Fourier? We can only use Laplace in this case. Only use Laplace because it's not sure there are initial conditions there or not, right? And if suppose this is u of minus t and this thing is not there, if this thing is not there, this is like this, but this is u of minus t. We can only use Fourier, we cannot use Laplace. All right. So they in this one they're asking the transfer function is given, and you would like to find the output. So since this is actually output over input is equal output over input, we have the input here, but in time domain, we'll take this into frequency domain, the Fourier domain, and multiply cross multiply into this one. We'll get the output. Okay. All right. Everyone okay? Raise of hands. Why can't I see the? Today is very slow. My end. Can I have a raise of hands? Oh, okay. Good. Thank you. मैंने कैमरे बंद कर दिए. ठीक है. All right. So let's take a look at one of these circuit questions. Which one do you want me to do? This one? This one or which one? I'm not doing it. I'm just trying to, explain it here. Conversation. All right. So maybe, yeah, okay, this one. Apparently, it has two sources. Determine the Fourier transform of I naught t in the circuit of figure 18.4. By the way, guys, please make sure that the final exam is not an exam. It's a take-home exam. It's an extended assignment. All right. An extended assignment is not a classical final exam. Don't expect question determine the Fourier transform of I naught t in the circuit. No. Maybe you can expect something like explain how we can have I naught t as the Fourier transform of something, something, something. Not the classical questions determine the Fourier transform. No, don't expect any question in extended assignment as straightforward. There should be some reasoning, some justification, and like everyone will have or may have a different answer, because it's like not just standard question, but it is some question that requires some of the thought process, right? Maybe for like for filters, uh, not like design a filter. It will be, will this filter be suitable for this particular application, and what is a suitable filter for replacing the existing filter, like this. So it will not be straightforward determine or find a design. It will be a case study kind of thing. So be ready for, and since we have one day, 24 hours, you can easily use the same skills. Eventually, you would have to find the Fourier transform. Eventually, you would have to solve a circuit. Eventually, you would have to design a circuit. But the thought process behind it will be given. Normally, in the questions, it is already given, okay, do this for this value and this value. But now you have to find those particular values for a particular design problem. All right. So this is one tip for the extended assignment, which is 35%. Yes. All right. So in this case, you have to find I naught t. Okay. It's again not a straightforward question, but not difficult as well. You basically have to convert this into Fourier domain. So you need to convert this into Fourier domain. So 1 upon 4 and 2 and this, these will be going into Fourier actually basically this one, e to the minus t ut and 3 delta t. Luckily we have the Laplace tables and this one to find the Fourier transform of this, and then finding the voltage maybe here, so V minus this upon this and this. So these, and remember 1 upon 4 farad capacitance will be, remember 1 upon j 1 upon j omega xc, 1 upon j of this thing and j2 omega of this thing. So these will be in complex numbers. So once you have the equation correct, so this is just one equation needed because there's just one node. We can find the equation, and once we have V, we can find I naught by V upon the reactance of this inductance, and we get I naught, which will be in frequency domain. Okay, so we don't need to find I naught t here. You just need to find I naught I naught omega, which is in Fourier domain. If they ask you to find I naught t, then whatever you get for I naught omega, you have to take inverse Fourier to get I naught t. All right. So we won't be going into complicated circuits. The idea is to make use of the Fourier transform in some way that shows that, okay, you know how we use Fourier transform in circuits, how to transform some particular signals into Fourier domain, and then find the equations, solve them, and then depending, like this one, V naught t. We want to find V naught t. So once we have V naught t, which is like this node voltage, V naught t, V naught omega, we have to bring it back into time domain. This one, no need, because Fourier transform, we actually need I naught omega. Here we need V naught t. Here also, it's like IT in time domain. So once you have the final I omega, you have to convert it back in time domain using inverse Fourier to get IT. Find this also. Okay, but yeah, by the way, V naught t at t equal to 1 second. Can someone, okay, just can someone explain to me how are we going to do this question? Let me ask Jocelyn, because she already has done this question. Jocelyn, can you tell us how will you be solving this question?
At t equals to 1, the V is equals to 10. Then we will use the voltage divider rule to find the V naught, and then we transform it back to.
Oh dear. Oh dear. Oh dear. Okay, wait. This is V naught and this is Vs. This is V naught and this is Vs. Do you want to rephrase your answer?
Yeah, my answer should be V naught equals to 10 at t equals to 1. Is it?
Okay. No. Wait. All right. Let me. Someone else. Maybe someone else want to chip in. Anyone else? Anyone? All right. We go with the normal flow. Like, Vs, we take it into Fourier domain. This will be in Fourier domain. And we start writing the equation. This is V naught. So this is V naught. This is also V naught. We write the equation in terms of V naught. We find V naught omega. Okay. So we find the Fourier transform for this one using the approaches that we have already learned. Once we have the Fourier transform and this, we convert this into j omega like this, just j. We will find v naught omega. Once we have v naught omega, we will convert it back into time domain v naught t, taking inverse Fourier. Once we have inverse Fourier and we have v naught t, we put t equal to 1 in that expression to get the v naught at t equal to 1 second. See, it's not difficult, but you have to look at the question properly. Jocelyn?
Okay, thank you, sir.
So don't rush. This is very simple again, but if you rush it in a way, I'm going to scratch my remaining here. Okay? Anyone, any question? If there is no question, can I have a raise of hands from everyone? Three, still 23. Mustaqim, Nabihan. Mustaqim, are you following? Is Luqman here? Luqman, are you following? Luqman, I know you have raised your hand. I want your answer as well. I want to hear it from you. Luqman, are you there?
Yes, sir.
Okay, are you following, Luqman?
Yeah, I'm following.
All right. So let's break out into the channels and do the normal, the new normal, and I will visit to different channels, and in a while Romesa and Yasser will also take care of those channels. Is Faraz here? Faraz is not here. Yasser, can you check Faraz to also join and see if someone needs help? Let me know. Next week, Monday morning, we'll try to have a session, especially for those who want special help. Don't hesitate to join those sessions. And I would like, especially those who have test marks less than 50% in that particular session. Okay, so Monday. When is the test, by the way? When is the test? Next month, like coming Monday, right? Which is 17th August. August 4 p.m. Test 2, chapter 3, 4, and 5. Okay. So maybe Monday morning, the 8:30 a.m. session. Please, especially all those who have test 1 scores less than 50% or less. Actually, no, 60% or less. I want all those to be there, say in the morning session, and they should have, each one of them should have one question to ask. Okay, this is like compulsory now. All those who have test scores 60% or less should be joining the Monday morning session with at least one question which is half cooked or like half done, where they got stuck. Okay, go through the homework problems, do the questions, and see if you can find a problem that gave you a problem, and you should ask me. Okay, I wish I could open the score sheet here, but everybody will see it. By the way, you can see your grades. Let me show you that you can see your grades actually. Have you seen your grades so far? How? There should be a way to see the grades somewhere. So far, we have like officially 7 quizzes officially. We'll just take the best 5 or best whatever. But where do we see the grades? So I can see the grades. This means you can also see your grades. Okay, I'm just scrolling so that nobody can see what's happening. But you have to see your grades, and maybe I'll send a form that you have seen your grades and is okay. All right, so break out into your channels. One more reminder, very important. Tomorrow, 2 p.m. reminder for an adjunct lecturer from Petronas, senior engineer Fakhr Razi. He is the plant manager at Petronas Malacca. And once again, you can ask about Petronas, about the oil operation, about industrial problems, the life in industry, how to get internship, anything. All right, so tomorrow 2 p.m. Probably I'll be conducting the session from site. Yes. All right, thank you. Break out into your sessions, and maybe we'll join back at 3:30 in the main general channel. All right, go.